Neural networks and more in general deep learning make up a foundational part of both AI and machine learning. We will cover many of the essentials of neural networks where it comes to training, tuning, and readying a model for deployment. It is important that you keep in mind that for neural networks, there is often an opportunity cost when deciding to use them as the model of choice. The opportunity cost, or the loss of potential gain from other models, will become more apparent as you begin to grasp the number of tunable hyperparameters that make neural networks so flexible and efficient. For certain applications like machine translation and speech-to-text, current trends indicate that it only makes sense to use a neural network. First, we will cover at a high level neural networks and their basic terminology. Then we will talk about the foundational architectures. We will then use the Avail-Churn dataset to demonstrate how to build a simple neural network using TensorFlow. Finally, we will provide some insight into regularization techniques, model persistence, and tunable hyperparameters. The multi-layer perceptron, or MLP type of neural network, can take a variety of shapes. In this example, there are 4 hidden layers, 4 inputs, and 2 outputs. Information flows in one direction, left to right in our graphic. Feed-forward networks can be seen as efficient nonlinear function approximators. Even in this relatively simple network, we see that there are a large number of weights, as represented by the directed edges. There have been numerous advances in the field of deep learning that go far beyond the architectures mentioned on this slide. But just these types of neural networks, multi-layer perceptron, autoencoders, convolutional neural networks, and recurrent neural networks, have an incredible amount of possible applications. There will be further advancement in the form of better learning algorithms, more data, and processing power that will encourage even more application of these basic architectures. Image analysis, natural language processing, and time series are areas of data science that have seen impressive gains because of recent advances using these networks, and the trend appears like it will continue. We update weights in a MLP using backpropagation of the prediction errors, which is essentially a form of gradient descent. The basic error function for the MLP is shown here. We square the differences between the predicted and observed outputs because we will be summing errors, and we need to avoid having errors in different directions that cancel each other out. Backpropagation, or the recursive application of the chain rule back along the computational network, allows the calculation of local gradients. This then enables gradient descent to be used to find the changes in the weights required to minimize the loss function. If you are not familiar with this general algorithm, we encourage a more in-depth treatment of backpropagation. We have used these data several times before. Recall how random forests perform. Let us use this as a base classifier to compare our neural networks to. Neural networks can be computationally intensive, and there are times where a GPU or another dedicated processing device will be needed. This function allows you to check the available devices on your machine. It also shows you the version, and there have been a number of API changes with the release of TensorFlow 2.0, so be aware that there may be differences when you use older code examples. Here is an example of a neural net implemented using the sequential interface of Keras. You may try to beat the random forest baseline by varying the number of nodes in each layer, varying the number of layers, changing the activation functions, or changing the loss function, and you will likely figure out a way if you try long enough. The Avail-Churn dataset, however, contained a percentage of churned subscribers who decided to churn completely randomly. That is, there is no known relationship to the available data. Given the limited amount of data, both in terms of features and observations, we can say the neural network and random forest models performed comparably. There are several methods to save your model. The first one here shows a simple method that saves a trained model. If you need to save your model during the training process, you can use the checkpoints as shown in the second code block. Note that it uses a callback option. There are a number of tunable parameters, and it is easy to sink hours into tuning and optimizing. The Keras wrapper class that is imported here is an extremely convenient way to get access to scikit-learn's cross-validation tooling. Some automation of the tuning process, especially with larger datasets, will save you significant amounts of time.